Hi,
Hi,
Yuekang. Hi, everybody.
can you see my screen now? Hi, Sheikh. Hi, everyone. Screen?
Not yet. Now it's coming.
Can you see my screen now?
Yes.
Stopped. Sorry, I try again. So you can see my screen now, right?
Yes.
Shall we start?
Yeah, we can start.
Okay.
Right. Okay. Hello, everybody. So I'll be starting the talk first, and then I'll hand over to Yuekang. Good evening, good morning, good afternoon, wherever you are. So we'll be talking about gray box fuzzing and how we bridge the gaps from the industry and academia perspective. Just short background on the collaboration. Continental started collaborating with NTU under Continental NTU Cop Lab from beginning of 2020. One of the work packages that we are looking into is how we can use fuzzing also for automotive and beyond automotive domains. And of course, we are looking at the white spots where we can generate innovations and also improve fuzzing activities, not only in automotive, but beyond automotive in other sectors like IoT, for example. Okay, so why should we even care about software testing or software quality? It is a big issue. I mean, I'm not talking about only automotive, but in general, right? So I recently read an article which is called "Era of 90s Defects," which is of course not focusing on automotive, but there was a statement where the writer wrote about software bugs which can cost companies 100 million. And now we are actually following the era of software-defined vehicles, which means that 5 years back or 6 years back, when we were talking about 100 million lines of code, now in the era of software-defined vehicles, so we will be talking about 3 times more, 300, 400 million lines of code. And we might get more than 90s defects when we don't follow software security guidelines, not only in automotive, but in the IoT sector, where we are talking about millions of IoT devices connected to the one gateway and so on. So the thing is, such type of domain, when you have any vulnerability or security aspects, then such recalls will definitely cost you millions. And of course, you can see a kind of a trend in the technology domain. A lot of compliance or regulations are coming in, and projects that we are dealing with have to meet those compliance or regulations and standardization. Therefore, customers will come to you and we'll talk about complying with software security guidelines and standards. And a lot of OEM are coming, coming with the requirements that they indeed need fuzz testing for the new projects. And there you have seen what are the advantages that fuzz testing provides. And Andreas talk from Cariad. And I think it was a very good talk to set the floor. And this will help everybody in this audience and also the other speakers to talk about it. Yeah, let's then focus on a little bit on the fuzzing part, a background of fuzzing. So basically, what is fuzzing? We already know from the previous talk. I don't want to explain more about it. It is actually about random inputs and testing the code's quality. In most cases, it is used for finding security vulnerabilities. Of course, it has a big advantage compared to static analysis techniques. It doesn't have such type of false alarms. Of course, if you don't prepare the inputs for the fuzzing in the right way, it could miss some bugs for sure, but it hardly provides you false alarms, which is the case in static analysis techniques. And it also has an advantage to generate what kind of inputs actually cause the crashes or the bugs in the software, and this is a huge advantage that we have also seen some example in the previous talk. Now, when we are talking about fuzzing, there are actually three types of fuzzing that we know of. First one is the black box fuzzing, which is highly scalable because you just don't have to have access to the source code. You just do fuzzing on the compiled code, and it doesn't require program analysis in general. But of course, in this case, your input has to be well prepared. Otherwise, it will lack. So the based on the I would say non-effective inputs, your output can be also a garbage in this case. Therefore, white box fuzzing could be of benefit. It's highly effective because you can actually fuzz the source code, and also you can take inputs from the and mutate the source code in general, and then but it could be very slow because you will be fuzzing all specific lines of the code, and it also heavily depends on how you analyze the program. Of course, there are different techniques, symbolic code execution and such, which is highly effective, but it also not so scalable when we are thinking about 100 million lines of code or a full system fuzzing. Then it comes to a fuzzing. We don't have a fuzzing called black or white box, but we have another fuzzing that is called gray box. And gray box fuzzing is actually taking the advantage of black box and the white box, and those are quite scalable because you can actually set different pointers to the code, and at the same time it can give you feedback, and based on the feedback you can mutate the program in a way so that it will generate more code coverage at the end, and at the same time it will find more branches of the code and will find more defects in the code. So you can say it's a jack of all trades, but of course a master of none, because it definitely have some limitations, and those limitations we'll be focusing on today's talk. And with that, I will hand over to Yuekang, where Yuekang will talk about what are the different steps of gray box fuzzing is, and then he will highlight two of the contributions that we have made in the Continental NTU Corp Lab as part of our innovation activities.
Hi, thanks. Thank you, Sheikh. And I will introduce you the meta model of gray box testing or fuzzing first. So this meta model is very easy, and we use this model to think about what kind of problems we can solve and what kind of improvements we can have. So this model starts from and describes how gray box fuzzing works. So the first step is we need to generate a lot of test cases, and this is needed for any type of testing technique. And then, because testing technique is a dynamic technique, dynamic analysis technique, it requires us to execute the target program. So we need to feed the test cases to the target program and execute the target program with the test inputs. And after that, we can collect and analyze the execution feedback. But that's not all. We still need to use the feedback to adjust the test case generation. So you can see that we form a feedback loop, and we can continuously improve the generated test case according to the feedback of the execution. And the feedback part differentiates the color of box. So if we use more feedback from the program, then we are more towards the white box analysis. And the scalability may drop, but the effectiveness may increase. And if we use nice feedback, um, then we are more towards black box testing. Then the scalability can improve, but the effectiveness may drop. So here are some previous works in academia. So in academia, previous works are mainly focused on test case generation and execution feedback analysis. For example, for generating test cases, there are existing works for using some grammars or models to generate test cases, especially for JavaScript engines. And for collecting and analyzing execution feedback, researchers have come up with different ideas of collecting different types of feedbacks. By default, one of the most popular gray box fuzzers, AFL, is using only the code basic block or edge coverage as its feedback. But we can also use other types of feedback, such as the value of an interesting variable, or maybe the state of the program. So we can use different kind of execution feedbacks, and we can collect different kind of feedback. However, target program execution is uh, kind of ignored in the research because it seems easier at first glance, because we just execute the program. What's the difficulty here, right? So it's less studied in academia. However, when we come to collaborate with our industry partners, we found that okay, there are actually two key challenges in practice. First, some targets need to be executed in emulated environment. For example, for IoT devices, for the firmware, we need they need some specific device to execute. However, it's not scalable because fuzzing, we want to have a high speed. We want to use some high-end devices or servers to run this fuzzing in parallel. But if we want, but if we were to run them on actual devices, then it's not scalable. We have to buy a lot of devices, and the computational power of those IoT devices are not enough for us to speed up the fuzzing process. So we need to emulate some of the targets. So this is the first challenge. The second challenge is some targets do not even have a suitable executables because like fuzzing, we need to really execute the target. But some targets, such as the libraries, they don't really have executable suitable for fuzzing. Or maybe there are some programs which involves a graphical user interface. Then it's not we cannot easily test those programs because we need to get rid of the graphical user interface to test the logic behind. So these are the two key challenges, and I will present you two of our works addressing each one of them. So the first work is emulation-based fuzzing. So just now I talked about a bit about the motivation from the industry perspective, because we have the software could be compiled for different CPU architectures, for example, for Intel, for ARM, or even for MIPS, and they may have different hardware dependencies. And most importantly, sometimes the source code may not be available. But from the academic perspective, we can see that, okay, there are existing works doing emulation-based fuzzing, but most of them are based on full system emulation. Full system emulation means that we are emulating the entire virtual PC, which has which includes the CPU, the disk, all the hardware and the OS, of course. So the emulation speed is very slow. So can we? The question here is, can we emulate IoT programs fully under user mode emulation? So this is our motivation from the academic perspective. So as you can see here, we are starting from a general problem, which is to do emulation-based fuzzing. And when we look into the academic perspective, when we really do some literature study, when we read some papers, we will come to some specific problems. So let me briefly introduce you our approach. And our approach is basically called observe and replay. The first step is we need to observe from full system emulation. We run the program on the test with a full system emulation once. And then what do we observe? We observe the dependencies of that program needed for user mode emulation. Such dependencies may include, but not limited to, launch variables, which includes basically environmental variables and dynamic files generated during the start of the process, and maybe some run config and some network behavior, because in this work we are dealing with firmwares running in routers, so and maybe some other process resources, some inter-process interactions with other processes. So these are the needed sources. So the first step is we observe the full system emulation and then extract the needed dependencies of the target process. And after that, we have a mapping between the dependencies and how we should deal with it in user mode emulation. So we can resolve all the dependencies during the user mode emulation, and we can do fuzzing fully under user mode emulation. And this can speed up the entire fuzzing process because we don't need to emulate the entire system. However, the drawback is we are not trying to find a perfect way of emulating any program under user mode emulation. We are only trying to do testing. So we are actually sacrificing some compatibility because we still cannot resolve some kind of dependencies when we transfer the program from full system emulation to user mode emulation. And however, we in exchange, we are gaining a lot of efficiency because the execution speed could greatly boost, as I will show you later. So now let's come to the evaluation of this work. From the experiments, we have found that okay, we have tried on nearly 100 firmware images, and we found that in this with our technique, we can execute the fuzz. We can speed up the fuzzing by 26 times comparing with full system emulation. And from the real world point of view, we have found 10 vulnerabilities which can affect 18 different types of routers, and 6 of them are assigned with CVE IDs. So that's all about the first work, which is about emulation-based fuzzing. Now let's come to the second work, which is called automated fuzz driver or harness generation. So fuzz driver or harness refers to the same thing. So in case you don't know what it is, I will quickly give you. I will give you a quick definition of what it is. So because there are because for libraries, for some programs, or especially libraries, there's no suitable executable program. In order to fuzz these library functions, we need to create a small program which can correctly invoke the library APIs in order to test it. So this small executable program is often called a fuzz driver or a fuzz harness. So the problem we observed from the industry practice is that um, programmers they don't like to use fuzzing in real practice. They don't like to use fuzzing when they are developing their software, because not because the current fuzzers are not strong enough to find bugs. It's not because of that. It's because they don't want to spare time to write fast drivers. Because in their point of view, writing fast driver is just an overhead. Because if I'm a developer, I will think that, okay, I've done enough of development. Why should I care about testing, right? So this is so writing fast driver is often an overhead for software developers, and it is important because most of the programs are not suitable for fuzzing by default. They need to somehow convert the program to a smaller executable which is suitable for fuzzing. So this is the problem here. And the second problem is, even though some developers are willing to write the fuzz driver or fuzz harness, they don't know how to do it effectively because they don't have security background, they don't have testing background. So, or maybe they are not familiar with the project. They need to learn a lot to learn how to use the API functions correctly. So this is the second problem hindering the testing or applying in industry practice. So from the academic point of view, there are existing works on how to generate fast harness or fast drivers automatically. However, they don't they have some drawbacks. The biggest drawback is that existing techniques uh, doesn't try to deal cannot handle control flow very well. By control flow, I mean it's like if, else, and loops. They are not handling this kind of program features very well. So this is the biggest issue. And as you can see, again, we are starting from a general problem, and and when we look into the academic point of view, we are coming to more specific problems. So our basic idea of this harness generation is that we have a target library, and we have a set of consumer programs using this library, and then these consumer programs may not be it may not be a suitable target for fuzzing, of course. So what we can do is we can learn how to invoke the library functions correctly from the consumer programs. And what we are learning here is an automaton which can represent the correct usage of the API functions, because library APIs may have dependencies. They may have different control flow or data flow dependencies, and maybe we need to invoke the API functions in a correct order in order to test it properly. So this automaton can describe this the dependencies between library functions. And after that, we just convert this automaton into fast drivers into the small programs needed for fuzzing. So this is our approach, and we have done some experiments on Java projects, and we can see that we can have improved coverage and bug detection compared with manually written harnesses. And for real world impact, we have reported 151 bugs on 9 Java projects and received 3 CVEs. So just now I introduced two of our works, and in fact, following the big model of testing, we have developed a set of techniques which are all published as research papers uh, uh, in uh, in academia. So you can see, based on, we can use this model actually to tackle new problems. Uh, I saw there are some people asking about protocol security or protocol fuzzing in the previous talk, and actually we can also use this model to think about how we can have improvements for protocol fuzzing, because it's also a very hot topic in academia. So for example, we can think about, from the input generation point of view, we can think about, okay, how can we generate valid packets communicated between the different parties of the protocol, right? So if the protocol is not open source, how can we learn the packet structure from the traffic, maybe? So that's one point of one improvement maybe we can do. And the second potential improvement is that maybe for executing protocol programs, we can improve the we can increase the execution efficiency, because we don't want to start a server every time for testing, right? We may want to start the server from a state, and then how can we do snapshot of the server? How can we fuzz it in a persistent mode? Is a problem. And actually, there are existing papers published discussing these topics. And of course, feedback collection, because most of the protocol bugs may not result in a crash. We may need to somehow observe we may need to introduce some other ways to observe bugs. And as for the feedback for guiding the fuzzing process, using the basic block level or edge level coverage feedback is often not enough to really drive the entire fuzzing process, to really drive the protocol from one state to another. So we may need to think about how can we use program state to guide the entire fuzzing process. And that's all about the tool works and how we can use the meta model of fuzzing to think about new problems or new improvements we can do. So now let's come to the conclusion, and Sheikh will give you this conclusion.
Okay, all right. So you can hear me, right? So
Yeah.
yeah, so the last slide, what Yuekang presented, kinds of draws me into the conclusion that yes, of course, there are a lot of fancy approaches and nice tools around, but we should always rather think about real world industrial problems around on the fuzzing or dynamic analysis part, and then we think about what are the research approaches out there. Are they fulfilling my needs? And then we come back to real world application. We try to implement them as we have also um, uh, 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 implemented a fuzzing prototype system in Continental together with NTU, and we kind of use our these innovations that what Yuekang has presented, integrated into such solution and try some real world applications and try to enhance them because unless you are testing them, verifying them, validating them on the real world problems, you don't know how they are performing. So real world pilots and use cases are the key if you really want to you really want to generate some effective solution in the dynamic analysis while you're using fuzzing. Um, so that concludes our talk, and we'll be ready to answer your questions, and also nice to have your comments as well. Thank you.